Right, let's see about the difference between a point and a vector. The secret is that there really is no difference. Any point is a vector. Any vector can be seen as a point. The key is that there's just two different ways of looking at the same thing. So here's a classic example in R3. Uh, a point P, which is given by the three coordinates 3, 5, 1, means that you go 3 in the x direction, 5 in the y, and 1 in the z. And you can also see that as a vector, 3, 5, 1. There's a couple of ways to write it. Vector x, I put a little arrow above the x. Whenever you see it in the book, it'll just be bold with 3 rows but only 1 column, so we call that a column vector. So why we have two different ways of looking at the same thing? Well, there's useful purpose in both. Points are better for describing a location, trying to tell where something is. The numbers in points, the 3, 5, 1, are called coordinates. Vectors are also fine for describing a location, as long as you know the context. But on top of that, they can describe moving in that direction, or the flow of something in that direction, or a force pulling in that direction. So once you draw an arrow from the origin to the point, you can pick up that arrow and use it to describe that particular magnitude and direction of force anywhere you like. So since it describes that kind of a thing, we call the numbers components in a vector, but the coordinates and the components, same numbers. We can add components to add vectors. That's the reason for calling them components. And you can scale vectors by multiplying the components. So here's how you scale. 2 times 3, 5, 1 is 6, 10, 2. Multiply each number by 2. And here's how you add. You just add the corresponding components. 3 plus 0 is 3, 5 plus negative 3 is 2, 1 plus 6 is 7. There's something that we won't use as much, but which will show up as parts of other operations called the dot product. So taking two vectors, and usually that's how we write them in Calc 3. The dot product is to multiply the components 0 times 3, the y component negative 3 times 5, and the z component 6 times 1, but then to add those up. So you get 0 minus 15 plus 6 equals negative 9. You can do a dot product with variables too, of course. Just let variables stand for the components x, y, and z. And then you notice that we have seen dot products. If you take the dot product of 3, 5, 1 with x, y, z, you get 3x plus 5y plus 1z. And that looks just like the left-hand side of a linear equation. So that means that we'll be able to use this idea to describe linear equations. This is a matrix 3, 5, 1, and 2, 0, negative 4 times a vector x, y, z, and equal to another smaller vector, negative 9, 2. But what it is it's a way to write the system. 3, 5, 1 times x, y, z gives you the dot product, 3x plus 5y plus z, and that's equal to negative 9. And then the second row times that column as a dot product would give you 2x minus 4z, and then set that equal to 2. So a matrix times a vector of variables is the same thing as a system of equations. So yeah, we could just go ahead and solve that system of equations just for practice. Turn it into an augmented matrix. which, if you looked up a little further, the augmented matrix is already kind of visible in the matrix times the variables way of writing it. Then do some row replacements. Row 1 replaced by row 1 minus row 2. Just to get a 1 there is kind of handy. So 3 minus 2, 5 minus 0, and 1 minus negative 4. And then negative 9 minus 2 gives you negative 11. Then replace row 2 by row 2 minus twice row 1 to put a 0 in that spot. Get a negative 10, negative 14, negative or positive 24 because that's 2 plus 22. Then divide the row 2 by negative 10. I just made them into decimals since dividing by 10 is easy. You get a 1.4 and a 2.4. And replace row 1 with row 1 minus 5 times row 2. So you get a 0 above the 1. Now it's in reduced row echelon form. So I think I turned it back into equations here. Yeah. So let's see. We had x1 minus 2x3 or y, x1 minus 2x3, or you could call them x, y, and z. So I used x1, x2, and x3 here. So x1 minus 2x3 equals that 1. Then x2 plus 1.4, x3 equals negative 2.4, and x3 is a free variable. Doesn't have a pivot. And then we can solve and get x1, x2, x3 equals 1 plus 2x3, negative 2.4, minus 1.4, x3, and x3 is itself. Just to show the alternative, if we used x, y, and z, then we could say z was free and write it as 1 plus 2z, negative 2.4 minus 1.4z. Now this will always be given in the problem statement what variables to use, but I just wanted to go back and forth a little bit so that you can tell it doesn't matter too much. A specific solution means pick a value for z. So if you pick 0 for z, you get that 1 and the negative 2.4 for x and y. Finally, there's a nice way to write the general solution as vectors. You can say that the vector x, y, z, or it could have gone with x1, x2, x3, is equal to the free variable times another vector, which would be the coefficients of the free variable in that way of writing it with equations. So I have z times 2, negative 1.4, and 1. And then add on the specific answer, which would be just the constants in the original equation answer, 1, negative 2.4, and 0. But it is the same thing as specific equation if you picked z equals 0. Now, this version of the general answer for a system is called a linear combination of constant vectors. It has one variable, that was the z coefficient, but in general you could have one variable and a vector for each free variable, plus that one final constant vector with no variable.